Now let's go ahead and take a look at an important property for surface integrals that's actually an extension of line integral properties. If you take a look here at the fact, notice that we can say that if our surface sigma is a finite union, it's a collection of a bunch of separate surfaces, we would say that sigma is piecewise smooth. And it would then be the case that if I wanted to do the surface area, or sorry, the surface integral over sigma, I could instead say that that's equivalent to a bunch of separate surface areas all added together. All right, let's take a look at kind of what this would look like in example number 5. Suppose that sigma is a can without a top, which consists of one surface, sigma 1, and a second surface given by this. Okay, so I have a sigma 1 and a sigma 2. First, I'm going to go ahead and just try to draw out what this looks like. Okay, so I'm going to go here and sketch out for myself some axes. So I have my x, my y, and my z axis here. So I'm actually going to go ahead here and take a look at sigma number 1. Now, sigma number 1 is given by some set of points that are determined by the following equations. Note here that I start with a circle. X squared plus y squared is equal to 1. All right, well, I can give a rough sketch of that down here in the xy plane. But I'll notice that I don't just draw it at the z coordinate of 0, but I can draw it all the way up until I hit a value of 2. So that is, I can go all the way until I get up to here at, we'll say, z coordinate being 2. Okay, so this here represents, I guess, kind of like the wall of the can. Right? This is my outer edge. There's no top. But then I also have this other surface, sigma 2. And sigma 2 is, well, it's not just a circle. It's x squared plus y squared is less than or equal to 1. So that means that I'm going to actually be dealing with this whole space down here. I'm dealing with the entirety of this bottom circle, and then also everything that has a smaller radius. And this is only graphed at the height when z is equal to 0. So what I can see here is that I have sigma 1 over here in blue, and sigma 2 over here in red. Sigma 1 represents the wall of this can, and sigma 2 represents the bottom. Okay, so the total surface that we're calling sigma in this problem is the combination of these two things. If I wanted to compute a surface integral then for sigma, I would need to compute two separate surface integrals, a blue one and a red one, or a surface integral over sigma 1 and one over sigma 2. So I could take a look here, and I could start to construct some parameterizations. All right, let's see. Find a parameterization for sigma number 1. All right, well, this actually isn't too terribly difficult to do. If I take a look here, one thing that I might notice right away is that I'm dealing with a circle type shape, and there's an easy way to generate a circle. I can do something with like a cosine of u, sine of u. This works out beautifully to help create circles. And I want these variables to be the same because they should have the same angle input to generate the circle. But it's this z value that can be something different because z is not related to the x's and the y's according to the formula. Now I can go, oops, I don't know why I drew a curly brace there. Now I can go ahead and actually put on some bounds here. I could state u here should go from, say, 0 to 2 pi because I want to go all the way around to create the full circle. And v can be bounded just as z is bounded from 0 to 2. Note that I can do something very, very similar when it comes to a parameterization for the sigma 2 that I have. And you'll notice here that I'm referring to this as s of uv. Okay, well, notice that if I started to try to do the same thing, cosine of u times the cosine of u and sine of u for the first two components, that would create a circle, but it wouldn't create the entire interior of the red space, right? It would only create that bottom edge of the can. So what I can actually do here is use my variable of v to kind of be the coefficients on these sines and cosines, which you may recall actually represents the radius of the corresponding circle. Just like up here, we had used a radius of 1, down here we're going to have a radius that is variable. Okay? That way I can kind of color in all possible radii up to a certain point. Of course, this is not actually going to be an issue when it comes to the z component, because here z is just always 0. So when I go ahead and sketch this out, I can still say that u has to go from 0 to 2 pi, so I can spin to get a full circle. But v now, representing the various radii that I need, can go up to a maximum radius of 1 to go out to cover the can, and I guess as small as a radius of 0 to shrink all the way down to an individual point. So these would be two perfectly good parameterizations that I could use. If you take a look at part C, I now ask, can you evaluate this surface integral? Well, as we had stated in the fact above, this surface integral should just be equivalent to doing two separate identical surface integrals. Well, I guess not identical because they're over different surfaces, but like the integrand is identical. So I have this integral over sigma 1, and then a similar integral, but just over sigma 2. So this would be the way that I would calculate it. Now notice, since I have two different parameterizations here, I would have to set up two different cross products and take two different norms and like set up the bounds are like a little bit different on each of the integrals. I'd have to set those up fully and do the calculations. Once I got an answer for each of them, I could take a sum total. What I'm going to ask you to do now is to go ahead, pause the video, and actually try to compute these out yourself. Okay? See if you can go through and do this. And then once you hit unpause, you'll be able to see me kind of briefly go through the solution. Okay, well, hopefully you did take some time there to figure out what these integrals turned into. Here is what I ultimately got from each of these. So first off, I'm just going to go ahead and note, and I'll skip a lot of the calculation here just for the sake of time, that my partial of r with respect to u crossed with the partial of r with respect to v, when I did that norm, I actually ended up with a total value of 1. Okay. When I did my partials and their cross product with respect to each of these variables for s, I ended up with a total result of v. Now, if you didn't get those, you could pause the video again here, try to go back, see how you might get to those answers. And if you need more details, you can always take a look at the full solutions posted in Blackboard. Okay, once I have this, setting up each of these integrals should become ultimately so incredibly simple. So you'll note here that my first integral is just going to be one that goes from, we'll say 0 to 2, and then 0 to 2 pi. The integrand here should just become 1 plus a v squared, because I'm going to have my sine squared plus cosine squared to get me the 1. And then at the back here, I'm just going to end up with 1 multiplied by, and I've set it up here as dv du. My other integral here, if I go from 0 to 1 and then 0 to 2 pi, again, here I'm going to end up with something very, very similar to before. I'm going to end up with a v squared for my integrand, and then this extra times v. And again, I have this set up as a dv du. Now, I'm not going to go through the calculation of each of these integrals, but I'll tell you the results that I did end up with. Okay. For each of these, I ended up with, let's see, for the first one, I had 2 pi times 14 thirds. And then on the other one, I got 2 pi times 1/4. And so I get a grand total here of 2 pi times 59/12, or that's the same thing as 59 pi over 6. Okay, so hopefully you were able to get to the same result. If there was any confusion again about either how I got those cross products or what happened here in the evaluation, feel free, go check Blackboard. You can see the full details. Okay. But what we're trying to drive home here ultimately is that I can deal with the surface integral that works with a surface made of multiple pieces. Now there's one other thing to kind of note here that we actually kind of glossed over back in part B. Back in part B, you'll note that we had to come up with a parameterization, well, because that's what we were asked to do. But did we have to come up with these parameterizations? Remember we talked about previously that you don't always need to construct a parameterization. Okay, well let's take a look at each of the surfaces. Part A, was that necessary? Well, that would depend on if sigma 1 actually was a function or whether it was not a function. And in this case, I can see that, yeah, this blue surface here would not pass vertical line test. It actually wouldn't pass a line parallel test with a line parallel to the y, z, or x-axis. So it doesn't meet any kind of function criteria, and this surface in blue had to be parameterized. However, take a look at sigma 2. Does sigma 2 have to be parameterized? No, it's actually a function that could be represented as a z equals function. And this is where part D comes in. Note that sigma 2 did not have to be parameterized, and it could have just been expressed as a function of the form z equals something with x's and y's. How could I go ahead and get the same result here? Well, let's see how this would work. So I could say that sigma could be seen as a formula z equals something. All right, if you go back to this surface though, it's actually almost kind of obvious what z should be here. If you look at any one of those red points, what can you tell about their z coordinates? Well, the z coordinates for every single one of those red points is always 0, right? Like they're always 0. So we're actually dealing with the plane z equals 0, but actually we're just dealing with a restricted version of that plane. So we're looking at z equals 0 over a region D. That is that circular region that we had, right? We had that circular region down there in the xy plane. But that circular region is actually super easy to define. So we let D be equal to, and I'm actually going to define this in terms of polar coordinates because that's so simple. R here could be thought of as going from 0 to 1, and theta could be thought of as going from 0 to pi over 2. And so if I wanted to, I could say that my integral over sigma 2 could instead be thought of as an integral over this polar region, or I guess over the surface z equals 0. And if that's the case, then notice that I would just be dealing with x squared plus y squared plus 0 squared. And at the back here, I have to do my r dr d theta. Now, of course, I still kind of have this hybrid integral form right now, and I would need to be able to replace this x squared plus y squared. That is actually super easy to do. Remember that I can replace that x squared plus y squared with simply an r squared. And so I end up here with just an integral of in r cubed, dr d theta. And if I was to evaluate this out, I'm going to end up with that exact same result, 2 pi times a quarter, or a grand total here of pi over 2. So what we can see again is that I could deal with surfaces that are functions either based on their function setup or as a parameterized surface. And either approach yields the same result, but it can be sometimes a lot easier to view a surface as a function rather than trying to deal with its parameterization. You'll notice the parameterization was harder to set up, it had a more difficult cross product to calculate, maybe even the resulting integral was slightly more complex. Although in this case it's not, because it ended up as the exact same integral with different variables in it. So these are all things to be thinking about and stuff that takes a little bit of practice to get used to. But hopefully you can see here that how we can deal with both functions and non-functions as well as surfaces that are made up of multiple pieces.